This is actually my first video in 2022, 2022, and in fact, it's the first time that I've filmed in 2 to 3 months, and I didn't actually think that was a very big deal. I figured I would just post when I could, but some of you reached out and it was just really sweet. I guess now that I look back in the YouTube world, I guess that's considered a mini hiatus, so whoops, I didn't actually plan for that to happen. Otherwise I would have told you ahead of time, but I didn't mean to cause any worry or concern or anything, but I really appreciate those of you who reached out and asked about my actual well-being and not only just pushed for new videos, but to actually just check in, which was really sweet. It was totally unexpected and I really just didn't think that it would be a big deal, but thank you so much, and here we are with another video, and I'm looking forward to this new year. But all in all, nothing dramatic happened or anything, which I am very grateful for, and I do know that that is more than a lot of people could say in 2021. So I am very grateful. I've actually been very productive during this time. So it's not just like I went off and took this huge break. But here we are with another math video, but I do hope that this is like a nice, just rambly, relaxing one, so feel free to just sit back. And also, I forgot to mention, if this is like the first upload, that you've joined, like if you've joined in the last 2 to 3 months, I wanted to send an extra special welcome, and if you've been around, let me know what you've been up to during this last chunk of time, and I figured we can catch up if you want over time. I'll share a little bit about the random things that are all exactly the same, and our three squares like we said. So the key properties here is, like we said, these are squares, so for each of these, the length and the widths are the same, and you can actually kind of see the x's here where I made sure that was the case when I cut them out. So these are all indeed squares, or as close to them as I could make them. And the other key thing is that I measured these right triangles so that, so since they're all the same, we'll just take this one, so that the one length matches this one, and so the two smaller ones match up like this, so the length matches this side of the right triangle. And then the pink one in particular is the longest one and matches with the hypotenuse, the longest side. So these sizes are not totally random. I made that in general, but the actual lengths themselves don't actually matter because we're just looking at the big picture here. So without loss of generality, is that without loss of generality, these can be whatever lengths as long as they are related in this way. So the four triangles have this as one side, this length as another, and then the pink one is the hypotenuse. The side here is the length of the hypotenuse. Okay, so what our goal is here then is to show that the lengths, so the squares of this, the square of the length of this side plus the square of the length of this side equals the square of the length of this side. That's the a squared plus b squared equals c squared. So c is always the hypotenuse. So another way to interpret squared is literally the area of a square. So that's the idea here. If we can somehow show that the sum of the areas, these two, equals this, then we are good. Then the area of this. But the problem is, if we look at this, we definitely see that this one is smaller than the pink one. But how do we show that the sum of like all of the rest of this pink area equals this? I mean, I guess you could kind of cut it and show that it is, but let's make use of these triangles that we cut in this way so that we have this side and this side. So let's go ahead and make use of them. So a fun little idea here is, and this is the main kind of logic piece of this visual proof, is we are going to consider this pink thing, instead of just using it as a square, we're actually going to consider it as the remaining parts of a bigger square. And same thing for these two. We're going to actually make a bigger square. Let me see how this goes. I'm just kind of winging this here, but we consider it as the remainder of a bigger square here. Let's see. Let's make it facing this. Okay, so let's make it facing one way. So if I make a square like so, like so, and so it'll kind of be at a diagonal here, like this, okay, like this, then you can see that we have a square, like so. Let's see, can you see that? So we actually have a square like this, this is like a piece in the middle of that. So this bigger square is because of the way that we drew out the lengths of each of these sides is A plus B, A plus B. So this is a square because we have A plus B, and then on this side it's B plus A. So which is the same as A plus B, so addition is commutative, so A plus B is the same as B plus A. So we have an A plus B by A plus B square. And these are all right because because these triangles are right triangles, so the angle is right, so that's why it's definitely a square. So we have our four sides that are A plus B by A plus B by A plus B by A plus B. So the total area is A plus B in parentheses squared. And we're just doing the visual part of this, so we don't have to actually do the algebraic calculation here. But that's what this bigger square is. So when I take away these four pieces, I'm left with this piece right here. Okay? And all we're really trying to show at the end of the day is that this area equals this one plus this one, so we don't actually have to care so much about what the actual, A plus B by A plus B squared looks like. That's just if you want to do the algebra. So what I'm going to do now instead is, so remember that this is kind of the remaining piece of my A plus B by A plus B square. Once I take away these pieces, this is like the in-between, like this is the inside in-between piece. That's the key takeaway, right? We're just taking these slivers away, and we are left with the pink one, and it is the diagonal by the diagonal. So what I'm going to do now is take this piece away, and I still have these four slivers, but instead I'm going to, so the areas are still the same, they're the same triangles, nothing happened to them, but I'm going to just play around with this and rearrange them a little differently. So instead I'm going to form these two rectangular pieces. And so now I have two rectangles instead, but it's the same four triangles from before, right? So nothing changed, it's just I'm going to match them up like this. So now when I look at these as rectangles, which they are because we have four sides and right angles, and we have A by B rectangles now. Again, by construction of the triangles, I have A and B here. So I have these two rectangles instead of the four triangles, but same thing. But if I place them like this is so interesting. If I place them like this, then I pop this right here, and I pop this one right here. Whoa. So now I have, again, an A plus B by A plus B square, A plus B, A plus B, A plus B, A plus B. So we have an A plus B square now. And again, if I took away the same four triangles, I'm left with this area, which is the same. It's the same resulting square when I did this one. So the remaining area areas are the same, and we didn't change the triangles at all. So therefore, the sum of the area of these two equals the area of this square. So like the area that it covers. Which by construction is this, the sum of these two squares. This is a by a, so this area is a squared. This is b by b, so this area is b squared. And then this would be c by c because this is the biggest one. So a and b are kind of arbitrary, but I made a the smaller one. But c is definitely the longer one, and so this is c by c. So the sum of the areas of these two squares equals the area of this square. Therefore, a squared plus b squared equals c squared. Isn't that neat? So it's just about playing with this area here. I can make an a by b square. A by b square. Like so. A plus b, but then if I rearrange these pieces, taking that away, I can again make the same kind of remaining part. I can make an a by b square in a slightly different way by rearranging the pieces like this. Shoop, shoop. So you can do the same reconstruction as long as your right triangles have the measurements, the exact measurements here. So they're not just any right triangles. They are a by b by, and therefore c. Ta-da! Is that not just the cutest proof ever? Cutest little visual proof here. So, it has to do with interpreting areas of squares and creating a larger one and looking at the leftovers. So anyway, this was a fun little way to come back, and again, we'll catch up as we go. Let me know what you're up to. Thanks so much for hanging